Hello, my name's Mike Batty. I'm sorry I can't be at the Elife conference. When you see this video, I'm probably going to be in Australia. But the organisers asked me if I could make a short video of the material that I would have presented, which is on big data, and in particular big data about cities. So what I will do is I will go through the PowerPoint, which you can see, and indicate various points that I made, show one or two movies if I can, and really sort of deal with the issue about big data, what it means for cities, and indeed what it means for thinking about animating and understanding movement in real time. Okay, an outline of my talk then. I want to really make the point to begin with about big data itself. What is big data? How big is it? And also to make the point that big can be small and small can be big. Big data is not new. It's new in the sense, it's only new in the sense that these large streams of data are being continuously generated by sensors in the environment, etc. The sensors may be mobile, they may be mobile phones, for example, or they may be fixed sensors, etc. But nevertheless, the era of big data really relates to real-time streaming of data. But big data, of course, in volume terms is nothing new, and it's all relative in the sense that we'll see as I continue that my definition of big data is relative to our ability to actually handle it, and that obviously relates to the methods that we have at any particular point in time, and indeed the computational facilities. Okay, I'll move on from a few of these general points to looking at some examples of what appear to be big data 100, 150 years ago in Ireland, for example, flow data. And then I want to point to an example of big data in the mid-1950s and refer you to a YouTube video. I'll show you very briefly a clip from this, but we won't see the video. And then I'll pull this stuff together and talk about how we make sense of data. I'll introduce the geographer Brian Berry and what he did in the 1960s and the data cube. And then the rest of the talk is really going to be about my definition of big data, which really is movement data or interaction data. One of the things that blows up data in terms of size is to deal with interactions. So my own view about cities is that they're not just locations, which is an old-fashioned sort of concept. They're really to do with interactions. So locations and interactions are two sides of the same coin. And I'll be dealing really with flow systems in cities. And one of the key issues that's been true for many years, indeed for over 150 years, is that we have great difficulty in visualizing flow systems because the data is truly big. I'll talk a little bit about the web and the desktop, how we're moving some of these ideas to the web in this particular context, and then say something a little bit about data in real time, and in particular stream data, again flow and movement data, and in this sense introduce our work with the RFID card in public transport in London, which is the Oyster card, and then a very brief point about reflections and conclusions. Okay, so data is big with respect to its volume. I know there are other definitions. There's the 3 or the 4 V's, basically, velocity, variety, etc. In this context. But to me, data is big if it requires a large use of the existing computer memory. This implies volume in some senses. And of course, as computers have changed, Moore's law, then clearly big data in 1955 was no longer big data in 1960. Big data in 2015 is going to be really probably small data to some extent in 2025. So to some extent, big data is relative in this sense. Now in cities, data usually implies numbers of locations. We define cities by defining them in terms of their locations. We measure their locations either as points of activity or indeed as aggregates of points into administrative units, etc. And so in some senses, our image of a city is of a series of locations. But locations imply interactions, and interactions imply relationships between locations. So if we have n locations, for example, as you can see, then immediately we have a possible number n squared interactions. And this to some extent gives cities their peculiar content. So small data in terms of if n is small can become big when we begin to look at n squared, and indeed there are sort of possibilities of n cubed and so on in terms of interaction effects. Here are some examples of flow data from Dublin in 1837, Ireland in 1888, and then London in 1953. And this is the oldest flow map. The oldest flow map we've ever discovered, in fact, is this one on the left, which was actually prepared by Lieutenant Harness, who was part of the British Army in 1837. Of course, at that point, Britain controlled the entire island of Ireland in this sense, and they were thinking about putting in railways in and around the Dublin region, and as part of this, Harness was commissioned to actually count, in some sense, the volume of movement, trips and so on, which was mainly freight in those particular days, into Dublin itself, as a basis for evaluating the feasibility of a railway. The map on the right is from Ravenstein. Ravenstein worked for the Royal Commission on migration in Britain in the late 19th century, and this is his map of flows, really. In some senses, this is a bit like a vector field map, in some sense, taken from his report. Ravenstein, I should say, is one of the first people to be credited with using a gravity model to actually explain and model this kind of activity. Now, I wanted to just point you in this direction to this YouTube movie. You can actually get it by copying that down, but if you simply type in the Great Railway Caper Big Data in 1955, then you'll get John Graham Cummings, and he's from Cloudflare. You'll get his explanation of big data then. To cut a long story short, the Lyons Tea Company, which was very innovative in computing in the early 1950s, had spare cycles for their computers, and they rented the space out to British Railways. British Railways wanted to price their freight, and to price their freight they needed a big network in terms of Britain, and they needed to actually handle the network. They needed to find the shortest routes through the network. In fact, in this particular video, if you click onto the YouTube thing, and I'm not going to at this point, it's going to take too long, if you click onto it, you'll see John talking about the challenges of putting this kind of data into core, using mercury tubes, etc., for the computer in terms of memory, and also punch cards and so on, and in and out memory all the time in this particular context. And also, in passing, this particular project invented the shortest routes problem in 1955. Dijkstra's algorithm was invented unwittingly by these researchers. Of course, Dijkstra didn't invent or didn't publish his algorithm until about 1959 in this sense. So again, interesting how big data in 1955 led to innovations in method. Okay, now let me make sense of data in this sense, and a good way of thinking of it in my world, where space and time are really very important in cities, is to think about a data cube. Back in 1964, Brian Berry, who was in the vanguard of the quantitative geography movement, wrote a very interesting paper where he looked at the dimensions of data for urban systems, and in particular he looked at the two-dimensional relationship. You can see this two-dimensional matrix or table basically between location and attributes, and he also suggested that this would blow itself up into big data in a sense if we added time. And you can see that the time is in discrete units to some extent, time slices, etc., largely because in the kind of world of cities that I grew up in, and the kind of world of cities that most theory of cities is all about, really suppresses time. We look at cities in equilibrium. We look at their attributes and their locations. We look at their flows, for example, but we don't really look at how they change much over time, largely because data has not been available. Of course, the era of big data has changed all that, and we have extremely rapid changes in time in cities which are measured from sensors over much shorter periods than people have thought about with respect to cities previously. So this is Brian Berry's data cube. It's what's called a data cube within computer science. Okay, let me move on very quickly to locations and interactions, flow systems in cities. Now, you've already seen a little bit of this, but we're talking here about big data being generated by flow systems. Now, here are some examples of flow systems historically. This is taken from my book in 1976, Urban Modelling, Cambridge University Press, and you can see that these diagrams at the top, which is locations in central and northeast Lancashire, north of Manchester in Britain. This is the central northeast Lancashire region, basically, with Preston, Blackburn, Burnley, these old cotton towns. And you can see the journey to work and journey to service flows being plotted. Of course, painstakingly, I actually drew these 40 years ago in this particular context. They're contained within the book. Now, you can see the bottom example of flows between 33 local authorities in London. And this is more recent data, of course. But you can see the problem of visualization. You can see once we go from n to n squared, then we have this problem of making sense of all these different flows. And you can see that where we plot, which is the second from the left at the bottom, that particular diagram where every local authority generates trips to every other, basically, where we plot the whole lot, then we simply get a mess. And one of the great challenges of flow data is to visualize it in appropriate ways. You can see here the Circos at the top left. The Circos software basically visualizes this flow data. The local authorities of London, the 33, are arranged around the circular edge, and their flows inside, which is a major problem, activity that flows inside the polygon or the area or the location is shown by these U-shaped things, and then the big flows across in this particular context. And you can see when we blow this 33 zones up to something like 633, which are the wards in London, and that's more or less the level at which we operate for land use transportation modelling. It's a bit coarse even at that level. We're probably talking really this region of Greater London should probably be about 2,000 zones for it to be pretty typical of the transportation models. Then you can see that it really does become problematic in terms of visualizing this big data. So if, for example, we have 1,000 zones in London, then of course we have 1 million potential trips in this sense from these origins and destinations. And that, to some extent, is becoming big data. If you think of big data as anything that would not fit into an Excel spreadsheet, and Excel spreadsheets have got to 1 million rows, so maybe we could, with 1 million zones, begin to look at this data in terms of that kind of software. In fact, if you packed a modern Excel spreadsheet with 1 million rows, then the thing would basically crash. So in other words, we are really at this point beginning to be in the area of big data. And it's big data which is actually collected through traditional means. Okay, now I've actually shown here some of the problems of big data. These are the predicted and observed trip distributions from a model, basically, a model, if you like, of trying to model these flows between wards in London. And you can see that here we've got something in the order of about 400k data points, and you can see immediately how potential statistics, traditional statistics begin to break down in some sense. You can see patterns in this data which are in some respects unconventional. You can also see the fact that with a very large scatter of points in this context, many of these points overlap each other. So simply to visualize the relationships in a sense, then we're dealing with a density of points in this particular context, and therefore our traditional statistics begin to break down. That most conventional statistics that we're still taught in universities and high schools and so on really are related to much smaller data volumes that we can visualize in this particular way. So even in this context here, and this is not big data in the contemporary sense, it's big data perhaps in the flow sense, and it's collected traditionally. Even in this context, some of our statistics are beginning to break down. Okay, so what happens when we really do begin to scale up in terms of these problems? Then we do really begin to get some major issues. What we're doing at the moment in CASA is building a land use transport model for the British Island, which is England, Wales and Scotland. What we're doing is we're building a model at the same scale as where you can see bottom left here, which is the Greater London Authority, really the inner part of the metro area in this sense. We're building a model for England, Wales and Scotland at this level of resolution. These are wards effectively, and what we're doing is we're using super output areas, what we call middle layer super output areas, and this is the zoning system. This is for England and Wales basically. There's 7,201 zones which lead to matrices of flows of something in the order of 50 million in this context. So there are immediate problems of visualization. Now the reason why we're building the model at this scale is largely because the potential stakeholders, the potential users of this model may be anywhere within Britain in this context. The reason why Scotland's not added, and that's an interesting point, is that the census data in Scotland is configured slightly differently, and when we put this thing together about a year ago, the Scottish data had not been released for the 2011 census. It is now, and we'll put Scotland onto this, etc. So in other words, we're building a model of flows between all of these small areas with an average of about 3,000 population in each in England, Wales and Scotland in this particular context. So this really is big data, and visualizing the flows is quite problematic. We need summary statistics to begin to do this. Okay, now the other feature of course is that we want to make this model available on the web. Basically we want users anywhere in England, Wales and Scotland to be able to use it, to log on and use it. So we have a web-based resource in this particular context. The web-based resource, essentially the decisions to configure this are quite important, that we have lots of issues related to data on the and modeling and mapping on the server side and the client side. We have issues related to a queue of users basically interacting with the model from remote locations in some sense. So we have lots of issues particularly to do with a web-based service in some sense in this particular context. And we have these major issues about visualization, where we're talking about relatively big quantities of data being shipped across the web to the user, and of course interactivity. Okay, so 52 million cell matrices. These are things we have to hold in core, hold in RAM I should say. We probably have to hold 4 of these things in RAM at any one point in time. So far we've built this model based simply on the journey to work, but we're extending it to many other sectors. So every time we extend it to an additional sector, we have interactions between the origins and destinations, and then we have a whole variety of constraints and additional data which we really have to add. So in other words, we've basically built the model in its simplest form so far, and we'll be extending it by repeating its structure and building an integrated land use transport model in this particular way. Okay, let me move on to this. Clearly we have a number of clients on the server. I've really made all these points, etc. I'll just emphasize them again. The matrices are really too slow to download to the client. In some senses we do a lot of the mapping and the computation on the server side basically, and then deliver the results to the client. We do most of the mapping in fact on the client side using Mapbox and a variety of web-based mapping tools, etc. And in some senses there are some clear issues pertaining to how we configure this, which pertain to the speed and time and the ability to actually visualize quickly for the user in this context. So this, and if you log on to this particular link, if you do log on to quant.casa.ucl.ac.uk, then you'll get a version of the model. It's an alpha version basically still at this particular point. And we are using it to simulate large-scale change in the UK, such as the impact of new airports, new roads and so on, typically which are the kind of things that land use transport models are being used for. And in fact, what we're doing is if you log on to this, you will see some of the issues. You'll get a web-based resource, you'll be able to deliver. So don't log on in Safari, use Chrome and Internet and the latest version of Internet Explorer, and make sure that you're WebGL is active in some sense, which probably might need in Safari, for example, for you to click on one of the buttons in the preferences. Okay, but generally speaking, you should be able to get this working. Now, typically, this is the kind of thing we get. This is the local authority area. We plot these vectors of flows. You can see in this context, the plotting the flows from origins to destinations and taking the average. In a sense, we can do that two ways, both for origins then for destinations, which gives us some picture. Obviously gives us a picture of the orientation of Britain to some extent in this particular context. Okay, so let me stop at that point and introduce you to one more thing before I actually finish. We do have another project in CASA which is related to our Oyster card data, which is the tap-in, tap-out data that we get from Transport for London. Again, to cut a long story short, we have about 12 million tap-in, tap-outs per day. Transport for London deliver this to us in big tranches, so we have about 6 months data for 2012 over the Olympics. Of course, the tap-in, tap-out data, the Oyster card data, the RFID cards that we use cover about 85% of the use of public transport, and public transport is tube, overground rail, some network rail, and also buses. So about 12 million tap-in, tap-outs per day, and this gives us about 1 billion records. It's a big flat unstructured file, 1 billion records for the 6 months we have in 2012. Okay, I'm just going to show you some pictures here of this and show you what we can do. That's John Reeds, one of our researchers who's a lecturer at King's now. And I'm just going to show you very quickly. Let me just come out of this PowerPoint and see if I can actually pull up the the Pulse of the City movie. I'm not very good here. Let me just pull up. I shouldn't be doing this really. Now let me see, have I got it? Yes, okay. I think it's probably already loaded somewhere. Yes, it is. Okay, so I'm actually going to show you some of the flow data here, for example. Now, what we're able to do with this tap-in, tap-out data is we're able to actually build flow patterns between the origins and destinations, between the stations. Now, what you're seeing here, actually it's not working at the moment. Okay, we're now seeing it. So if you look at the little counter there, if you can see that little counter, it's counting down. We're on to Monday, 3 in the morning, 5 in the morning. Then you see the morning peak, basically, and then we'll see the evening peak. And then in the late evening, there's a little bit of a jump, which is the entertainment peak. Now, this is a synthetic 5-day data set. We've had to piece this together from the tap-in, tap-out stuff. We have to make lots of assumptions about shortest routes because particularly on the underground system, there are many ways of actually travelling between A and B. In this context, we don't know what these are. We have to make good guesses, basically using shortest routes things, and also some complexity in the subway stations themselves. So you can see we're into Thursday now. We're coming about Thursday, Friday morning, and then we're the Friday morning peak, and then the evening peak, which is different. And then the little late night entertainment peak at that point, and then we're into Saturday and Sunday, and it will finish. Now, a couple of points about this, in some senses. A couple of points relate to the fact that the data is very heterogeneous. It looks regular in some sense, and there is great regularity in it, but it's also heterogeneous within this regularity, and this to some extent is really one of the features of big data and new data of this particular kind. So in other words, the kind of trips I've been showing you earlier on, the kind of flows, etc., for Great Britain, etc., the journey to work, etc., this kind of data is enriching it in terms of looking at the heterogeneity, that when people go from A to B, they never go quite at the same time, even if they're in terms of a routine journey to work. So this is giving us a new dimension to the city in terms of big data. Okay, now I want to stop. I've been going on for about 20 minutes, perhaps 25, I think. And I'll just make a few points to finish. Big data is not what it seems. We've always had big data, and big data to some extent is big because of limits on computers. We've also found it difficult to handle big data in the past, and particularly we found it very difficult to handle data in any visual terms, and the kind of data that we're involved in cities, movement data, etc., is exceptionally difficult to actually visualize, even despite the advances in visualization that have taken place over the last 10 years. There are still major issues in terms of visualizing and providing the user and the analyst with information, with data in a form that is easily kind of graspable through visualization. The final point, I think, is that it's often said that big data requires new techniques of data mining, etc. And I think I've indicated to some extent in this talk that some of the ideas that we've had traditionally about thinking about data as scatter actually in space, scatter plots and so on, to conventional statistics begins to break down. Okay, thanks very much for your attention, and some acknowledgements to my colleagues basically, and those are my coordinates. Thank you.